Number 10 you didn't like. This is specifically helpful to you because number 10 you didn't like. Even though it's not a parent function like any other that you see in homework, well, besides number 10, it still is a parent function. It still is a parent function that you should be able to do transformations to, even though you don't like it. It still is a parent function that you should be able to do transformations to, even if you don't like it. So, to that end, not that one, that one. Okay, let's talk about it. Kiddos, I'm going to go ahead and color code mine too, just so we can be on the same page. So let me start off with red. All right, for letter A, what transformation is occurring? First of all, horizontal or vertical? Why? Because it's in the inside. Good, it's inside the function, inside the argument. So it's a horizontal, and what's happening if you're multiplying by a negative? Reflection or flip. Now, hold on. That's my silly way of saying it, but what axis are you technically going about if it's a horizontal flip? Does that make sense? So it's a reflection in the y-axis, or about the y-axis, if you had to make it all snazzy and official. Okay, so if it's a horizontal flip, all the right becomes left, and all the left becomes right. All we have to do is multiply each of our x values, our horizontal values, by a negative. So instead of positive 6, 2, what's it going to be? Negative 6, 2. Does that make sense? Instead of negative 4, 2, it's going to be to everybody. Horizontal flip means each of the x multiplied by a negative. Negative 2, 2 becomes positive 2, 2. Sorry, negative 2, negative 2 becomes positive 2, negative 2. And then 0, negative 2 stays the same. And we end up with somebody who's been flipped. My lines weren't perfectly straight. Yours might be a little bit nicer. Does that make sense, guys, how I did it point by point? And that might make a little more sense as to why on Friday, when I was doing parent functions, or I was using parent functions, I did some points. And I said, oh, hey, the points need to shift and then reflect. The points need to shift and then reflect. And I was doing things like subtracting from the x's and then multiplying by a negative to get my new points. So some of you might want to do like the actual moving of it, and some of you might just want to do different operations to the x's and the y's as you go. Now what's letter B? What transformation would this be? Vertical shift. So it's going to go ultimately up 4, right? Now up 4, what's being changed? The x or the y? Good, because the y's are the up-down values, right? So instead of being 6, 2, where's it going to be now? Up. It's going to be 10, not 10, as I was copying. 6, 6, yeah. Instead of 0, where is that? 0, negative 2, it's going to be 0, positive 2. Instead of negative 2, negative 2, it's going to be negative 2, positive 2. And instead of negative 4, 2, it's going to be negative 4, 6. And when you move it point by point, you maintain the shape, you maintain the size, and you do the transformation that you yeah? Now, is this going to start to get messy? Yes, it is. Could you maybe do a couple copies of the graph? Maybe on number 10 you didn't finish it. You weren't quite sure what to do. You could make this graph a couple different times, or you could do a different graph for each and every one. That's totally fine also. I'm just trying to simplify the process a little bit by doing multiple on the same one. However, for sake of illustration, I am going to run out of space soon, so I'm going to go ahead and do a little copy, a little paste for probably the bottom 3 or 4. But let's keep going with letter C. I think I can do a couple more without messing it up too much. Letter C. Vertical or horizontal? Shift, stretch, or reflect? Stretch, or dilation technically, by a factor of 2. So it is going to be a stretch because it's by a factor of 2. What's this one by a factor of? Horizontal is always different than you think. It's going to be a half, 1/2. It's flipped. Good. So this is going to be vertical by 2. Vertical by a factor of 2. Vertical stretch by a factor of 2. This one would be a horizontal shrink. Horizontal shrink by a factor of 1/2. So wait a minute, vertical, that we're doing it to the y's, right? Okay. So if it's by a factor of 2, doesn't that mean multiply? Okay. So instead of 6, 2, what's it going to be now? 6, 4. Good. So we're going to have 6, 4. Instead of 0, multiplying the negative 4, if I can get it to be on the actual line. To have negative 2, negative 2. Exactly. And instead of 4, 2. Negative 4, 4. And then when you connect, it will truly be stretched by a factor of 2. Not shifted, not reflected, but stretched by a factor of 2. Now this last one's going to be a little bit messier, but I think we can still do it. Let me get like some sort of random, I don't know, purple pen. There you go. There are a couple different transformations going on in this one, right? What do we have? It is going to be right 4, and it's going to be reflection in the x-axis, which is similar to a vertical flip. Same thing as a vertical flip, right? So vertical flip, which is in the x-axis. And then shift right 4. Vertical flip, shift right 4. Okay. Technically, vertical flip would come first. I was thinking PEMDAS, we would deal with that guy and then that guy. So vertical flip, then shift right 4. Vertical flip, what's going to happen to all of our x's? Sorry, all of our vertical, all of our y's. What's going to happen if they're flipping? Instead of being negative 4, positive 2. Negative 4, negative 2. Now, are you guys okay if we do two things at once? If 4 goes to negative 2, and then it's going to shift, y. It's opposite, and the x adds 4. Y becomes opposite, negative 4, negative 2, and the x adds 4. So we end up at the point, if I can get it, negative 4 plus 4, and then 2 times the negative. We have 0, 2 as our first point. 0, negative 2 is our first point. This one, same thing. We're going to add 4 to the x, so negative 2 plus 4 is 2, right? And we're going to flip the sign of the y. So it's going to be 2, 2. Adding 4 to the x, multiplying the y by the opposite. 0 plus 4 is now 4. Flipping as well. Adding 4 to the x, multiplying the y by the opposite. And last but not least, adding 4 to the x, 10, and then making the y opposite, 10, negative 2. And now, we should have not only the vertical flip, but also the shift. What's the point of this? The point is to show you guys that with parent graphs, some of you were like, I just need to have this magical picture of a parabola and then do all these transformations. But if you notice, I was using reference points of every parent graph from section 1.6. I was using reference points, and I was using those points to shift and then connecting. And that's exactly what they're trying to show you here is, hey, sometimes it's easier to go by points. It's good to have an idea, but it's good to use points to keep your bearings, okay? Kiddos, let's just talk through the last few. I'm going to use my same colors. You can use different colors. Just now we're down to E through F, so we're down here. So on E, let's just talk through what we would do. Is that okay? Oh, purple. I don't want purple. What kind of transformation is going on in E? Down 3. So to do down 3, aren't we going to do each of our y values, take away 3? Does that make sense? Every single point, take each of your y values, take away 3. What about in this one? What about in this one? It is going to have a vertical flip, and then it is going to be, or it does have a vertical flip and down 1. Which order should you do it in? How could you check? If you ever get stuck by the order, whether to go down 1, then flip it, or whether to flip it and then go down 1, couldn't you always make a little table and just see? Couldn't you make a little table and couldn't you see? For instance, if we were to plug in 0, when x is 0, to our transformed one, which would be negative f of x minus 1. Wouldn't that be negative f of 0 minus 1? And then couldn't we plug in negative negative 2 minus 1, which ends up being what? 1. Okay, so let's check it. If we would go up to 2 and go down 1, it would go to 1. Which one's right? The first one. And the first one said to flip it, read it in the order that it is, to do a vertical flip and then a translation down 1. So I'm going to go ahead and write that just to help us out. It's going to be a vertical flip followed by, I think is how last year's book would put it, then a shift down 1. A vertical flip followed by then shifting down 1. But do you guys see how I just took a point and I plugged in? And I was like, hey, what happens to you? Oh, all right, fine. So you must have done a vertical flip and then down 1. Vertical flip and then down 1. Vertical flip would be 2 and then down 1. Vertical flip. Yeah, vertical flip and then down 1. Yeah, it'd be 6, negative 3, right? And it'd be negative 4, negative 3, etc., etc. Right, that's a cool little trick I've found just for me to double check real quickly that I have the order correctly. And then guys, what was the transformation on this one again really quickly? Horizontal shrink. Good, good, good. By the reciprocal, which would be 1/2. Which means that we would take, horizontal shrink. We're not touching the y's. The y's stay the same, but what are we doing to each of the x's? Multiplying by. Dividing them in half, which means multiplying by 1/2. Does that make sense? Dividing by 2 or multiplying by 1/2. Kiddos, I think that will really help you on number 10. So we are going to peek at the answer to number 10. Let's go ahead and get to the evens in our homework spirals. It's going to be on the video if you want to access it again tonight just to spend a little more time on it. We're not going to spend a lot of time on number 10 besides my just getting it on the video. Because some of you honestly just need to think through it a little bit more because you didn't quite have enough background knowledge. Or it was just a little bit too tricky for you when you went to go try it. You're got like a mental block going on. So we have our section 1.7. Let's check our evens, just peeking at I think number 10 is at the very bottom of the homework if I remember right. 1.7, right? Oh no, he's in line. 4, then 2, then 3, then 1. Does that match up? 4, then 2, then 3, then 1. Let me know if something looks funny. I'm going to get back to number 10 in a second. Let's go to number 46, just because number 10 has a lot of pieces. Number 46, the parent function was square root of x. Do you see why this was a horizontal shrink by 1/3? It was inside, so it was backwards what we thought. It was 1/3. A shrink followed by a shift upward, 1. And then this last one is just asking for parent function notation, like how could you look at it? I think last year's Algebra 2 book did a good job of showing you this. A g of x is, take out the square root, make it f of, and then show the plus one on the outside. And if you guys are wondering, just from what we've done today, can I show you how I would have done this graph without my calculator, just real quick? What's the parent function of radical x? But what swoop? Give me 3 points. What's the square root of 0? Okay, so I have the point 0, 0. What's the square root of 1? Okay. What's the square root of 2? Square root of 3? Square root of 4? See why I go to 4? Why am I showing you points? Can't you do this with points? So how could you do this or get that? Well, all the y's add 1, and all the x's get multiplied by a third. So if you want, you could even make a baby table in the sense of what the new points would be. So the old points are 0, 0. So you g of x. You had 0, 0, but for g, we're going to go ahead and say, hey, theoretically, you can think of just plugging it on in. But for g, you could say, okay, horizontal shrink, 0 gets multiplied by a third, which is still 0. And then y's get shifted up 1. Does that make sense? And then take the next point. Take 1, 1. What do the x's do? Get multiplied by a third. What do the y's do? Add 1. You can follow the pattern all the way down. What's the next point? 4, 2. What do the x's do? Get multiplied by a third. What do the y's do? Add 1. Then could you graph your 0, 1? Your 1/3 is now up to 3. And then 4/3, which is 1 1/3. Oh, sorry, 1/3 was only up to 2. My bad. And then 4/3, 1 1/3, was up to 3. Ugh, shh, pretend I did that properly. That should have been over a little bit more. But there you go, see? Swoop, there it is. Okay. Any more evens? 58. To do a vertical stretch, you had to multiply by 8 on the outside. To do a reflection in the x-axis, that would be a vertical flip, hence the negative on the out. And the vertical shrink multiplied by 1/4. The key would have been noticing the points and what the transformation was. The key would have been noticing the points and what the transformation was. Let's go back to number 10 before the word problem. Some of you guys are peeking at it. They did it 1 by 1 because it was so much easier as far as making it nice and neat, and they didn't have different colors in the answer key. So what I would do if I were you is first just check that you knew what the transformations were supposed to be. Shift everybody, right 5. Add 5 to all the x's. Reflect in the x, aka vertical flip. Vertical flip, and then shift 3 up. So multiply the y's by a negative, add all of them. Multiply all the y's by 1/3, exactly what you expect. Reflect in the x-axis, vertical flip, and then go right 1. Left 1. Flip everybody, horizontal flip. Reflection in the y-axis, which actually I think ends up being the same because the points were symmetric. And the last one was a nice one. Just shift everybody down. Sorry, there's a G too, isn't there? Okay. The last one would be stretch. Why stretch? It's backwards what you think. It's not by a factor of 1/3. It's by a factor of 3. So all the x's got multiplied by 3. So what was at 3, 0? Negative 3, 0 is now at 9, 0. Negative 9, 0. What was at 6? Negative 6 is at 18. The whole thing got whoosh, stretched like a rubber band. Stretched like a rubber band. Guys, this isn't the video. So if you got confused on number 10, take what we did on number 9, try it again tonight, and then go grade it and see if you're able to get it. Our last even, I believe, is the word problem, right? Number 70, were you supposed to do this guy by hand, or were you able to kind of use a graphing calculator? Well, didn't you have to plug in decimals? Like at some point you should have gone to your calculator, hopefully. Otherwise it would have been really, really messy. But what's going on with this is that it's just a parabola x squared that's been shifted right and been shifted up. But before both of those, you should have done the vertical shrink by a factor of, I know it's gross, but 0.068. So they show you the vertical shrink. They show you the reflection, the horizontal shift right, and the vertical shift up. So you could have actually done a quick little sketch. I think they actually just went to their graphing calculator to get the sketch itself. And then, wait a minute, who's this guy? Average rate? Wait, we've talked about it. Average rate is slope. And slope, back in the day, we said was f of x2 minus f of x1 all over x2 minus x1. But this time, we're not using f's. Who are we using? N, yeah. So n of b minus n of a all over b minus a, or n of x2 minus n of x1 all over x2 minus x1. It's an old formula, but with a new variable. Yeah, a new little baby twist because of they calling it n. They called it n and not f. But otherwise, you just got to plug in 10, plug in 3. Doesn't your calculator have a really cool little feature to plug in stuff for you? Especially if you just graphed it. So some of you might have used a little bit of Precal graphing calculator handbook stuff in order to help you out. Oh, now my computer's sad. And C is right behind. So final answer for the average rate was 0.976. In context of the problem, that would end up being 976,000 households. I think that was in millions or something, wasn't it? Number 76. Oh, what number is that? Oh, 70. Thank you. Millions. So since it was in millions, you would have had to take that number, the 0.976, and multiply it by a million. That's how you got thousands, 100,000, sorry. And then this one, you're just plugging in 18. Got it. The long story short is no, you could have had different reasons as to why it's no. But what I was trying to remind you guys of in your graphing calculator is if you did put that n of x into this function, which now it's a piecewise function, I'm not going to put it in, but if you were to put that whole thing in on the home screen, you could have done, check it, alpha y equals, cool little shortcut menu. You could have made a little baby fraction. This one's a great button. And you could have done your y1 of 10. Minus, oh yeah, it would have done all the work for you. y1 of 3, all over 10 minus 3. If you guys notice where I'm going to alpha and the button's up above. So alpha y equals n over d is that cool little fraction guy. And if I go alpha and then trace, I go to that y vars menu and I can use that. The parentheses is like function notation. It's super cool, super nifty. Mine will not work when I hit enter because, did you guys notice I didn't put anything in the y1? So it's going to be mad at me. Oh, plus I accidentally typed something in weird down there. I didn't mean to. But yeah, it's not going to like me because you do have to put the function in your calculator. But if you put the function in your calculator, that saves you a lot of time. Or it should save you a lot of time. Okay. Clarifications besides number 10, which you're going to go back and talk about, rework through tonight if you didn't get it last night. Evens or odds. Okay, just a few of you guys might need to rethink through that word problem just a little bit, but you're just going through the transformations. You're plugging into the slope formula using function notation, and then you're plugging and chugging 18 and interpreting it. Those are millions, and since it's 117 million, does the answer seem reasonable? The long story short is they say no because they're like the number of households should be increasing, so it should be going faster and faster, getting higher and higher. But there could have been different ways of doing that. I didn't see any other questions, so if you guys do have individual questions, feel free to come on in and let me know. During lunch, I probably have a student council meeting, but during period 7 or after school should be good. I'll be getting stuff ready for subs for tomorrow, but praying that I don't have to do it. Yeah. We already had the quiz, and we didn't use the calculator on it, right? It was by hand. Transition to notes, guys. And for the test, off top of my head, Kim, I don't remember any calculator problems. So there are some harder word problems in homework every now and then to remind you like how this applies to harder things, but on the test, I'm mostly testing the basic knowledge. Does that make sense? Like without the decimals and millions of households and things like that. Doesn't mean I'll never give word problems, but I think in chapter 1 there's so many little things, domain and range and even and odd and intercepts and transformations. I don't think I really take time for word problems. All right, kiddos. Section 1.8, combinations of functions. I'm going to let you guys go ahead and write this up. We start off by saying, okay, what if two functions have addition, subtraction, multiplication, or division, putting together something like an x squared and a square root of x, or an x cubed and an absolute value of x? What happens if we start putting them together? There's some funny function notation-y things. And if you don't write this down, you might get horribly messed up. Because this isn't f plus g times x. This is f of x plus g of x, a shortcut notation. It's not f plus g times. It's f of x plus g of x, f of x minus g of x. Let me give you a second. We're building up to compositions of functions, f of g of x. We're building up to that. But starting off with a tricky notation. The only one where domain might have an issue is going to be the last one, which is the division, because as soon as you divide, now you have a denominator. And we remember for domain problems, denominators can't equal 0, right, guys? But otherwise, besides that one, the domain should remain the same. So with all of these little formulas that you guys see, if they were to give us functions like the following, f of x and g of x, this is just as example finding the sum, f of x and g of x, and they were to ask us for, first of all, find f plus g of x, and then figure it out when x is 3. Our end goal is to figure out what is f plus g of 3. But this notation is super confusing to a lot of people. So we go back a step and we say, okay, what does just f plus g of x represent? And if it's just f of x plus g of x, according to our formulas on the page before, in order to work this out, all we got to do is say, who's f? This guy. Who's g? This guy. We can combine like terms. They just have little understood ones in front, so no signs are going to get messed up and no coefficients are going to get messed up. You're going to end up with x squared plus 4x plus 1 minus 1 is just 0. But then what does that mean for when we're supposed to do of 3 instead? Yeah, because you can think it's going to be f of 3 plus g of 3. That's one way of doing it. Or if you find f plus g of x, you could just say, hey, plug in 3. So it's going to be 3 squared plus 4 times 3, which mental math there. Does anybody get to 21 before me? But the notation is funny. That's why these formulas are going to be really, really helpful for you guys to have in mind. Now, domain problem. If we do have to do that quotient one, where we have f over g of x, and we can just use this same example up here. According to the formulas, does this mean we're putting f of x over g of x? We could just take the f and we could your 2x plus 1. G would be your x squared plus 2x minus 1. And that would be the final answer. But if they were to ask us domain, wouldn't we have to take our denominator? Ooh, maybe do some factoring also with the x method and say, hey, by the way, you're not allowed to equal 0. So remember, whenever you have a denominator, you have that extra domain problem of, because of the division, introducing an error or introducing a place where you could have some issues. Now, what we were trying to lead up to, and we just got to just now, here's a struggle because chapel day. Would have been fine if it wasn't chapel day. You guys don't need to submit pictures to this until Wednesday morning. I'll change the deadline in Google Classroom. Probably will not just, even on the video tomorrow, depending on what I show. We probably will not day tomorrow. We might go into 1.9 a little bit, just a heads up. So you might want to start homework tonight. Okay? But I'll change the Google Classroom deadline. F of g of x, remember the notation is funny. It's called a composition of functions, but didn't we say function notation shouldn't scare us? Whatever's on the inside just gets plugged in. So if we were to have something like our f of x over there, which I think was 2x plus 1, and our g of x, which was x squared plus 2x minus 1. If I wanted to find f of g of x, I would say I need to plug into f g of x, which means everywhere in f's x needs to go in instead. So I would end up with 2 times g plus 1. I go to f and I say, what's your pattern? The g needs to get inputted in, and then to finish off the problem, I would say, who's g? Oh, there he is. And then I would do a quick little, never mind, dot, dot, dot. Because how would you finish the problem? Simplify, distribute, combine like terms, etc. Guys, that really is the whole section. But there are some harder examples that some of you might get stuck playing things like bunnies and puppies. Sorry, not bunnies. This has to do with bunnies, but that's calculus and you won't see it until next year. Puppies. Don't kill the puppies or the seals. All right, kiddos, get out of here and definitely start 1.8. Some of you can bust the whole thing out. I'm going to make the technical deadline not until Wednesday. Sound good? All right. Bye, everybody. Lord willing, I will see you tomorrow. If not, well, hopefully I'll see you soon. Hopefully I'll see you soon. Happy Chapel Day.